All right, today we're going to look at ellipses. So this ugly looking shape is an ellipse. It's actually not an ugly shape, I just can't draw. So if you want a really good picture of this, take a look in your book. It'll definitely give you a much nicer idea of what this is supposed to look like. But so I just wanted to point at some of the important parts of an ellipse, and then we'll look at, there are two formulas that we're going to be using for ellipses, and the first one's already on the board. I highly recommend write those down or look in your book. Because I'll be using them as we go into the examples later. All right, so your ellipse, it's basically an elongated circle. It's an oval in a sense. An ellipse has a center, which I didn't label here, but it is this dot right in the middle. It has what's called a major axis and a minor axis. The major axis always runs through the ellipse the long way. So in just a few minutes, we'll also have an ellipse turned the other direction. And actually, I'll probably just let you look in your book to see that one. But basically, just rotate it and have it vertically. Then the major axis would be up and down instead of sideways. So here we have one where it's stretched horizontally. The major axis is horizontal. It's parallel to the x-axis. Minor axis is perpendicular to that. The vertices are the points at either side end of the ellipse on the major axis. And then in the middle, we have what are called these foci. So foci are just points in the middle, and they're really how the ellipse is defined. It's defined to be a set of points that is, whose distances from two fixed points is a positive constant. So these are called foci. So one thing that's interesting about ellipses is that they get used a lot in outer space. Planetary motion is all ellipses. If you ever see a model of the solar system and they're all circles, here's a hint. They're not. They're all ellipses. Some of them are closer to being circles than others, but they are all ellipses. And I believe it's the case that the sun is at one of the foci for the ellipse. And then everything goes around and around and around the sun. It's very fun, very exciting. So anyway, this is what our ellipse looks like. And here I have the formula and all the important information about ellipses when the major axis is parallel to the x-axis, like I have drawn here. So the formula is x minus h squared over a squared plus y minus k squared over b squared. A is actually the major axis length. Or, I'm sorry, it's half of the major axis length. A is the distance from the center to a vertex. That's going to be important here in a second. B is half of the minor axis length. It's the distance from the center to, well, the top of the ellipse in this case. It's not a vertex. Importantly, A is always bigger than B. And that's going to be important because in a minute when we get the other formula up here, we're just going to switch A and B, and that's going to be the only change. And so when you're looking at these formulas, trying to decide, is it a horizontally stretched ellipse or a vertically stretched ellipse, look for the bigger number. Because whichever one is bigger, that's going to be the direction it's stretched. So the center here is HK. I want to point out that just like with parabolas and circles way back in chapter 2, H and K make 0 inside these parentheses. By the way, if you don't have an H or a K, that means that you are centered at the origin. You have 0, 0. The vertices are going to be H, that center X value, plus A, right, that the distance to the vertex, and comma K, and H minus A, comma K. So basically start at the center, and you just go A units in either direction. The foci, we use C instead of A, H plus C and H minus C, where C squared is equal to A squared minus B squared, which is a little bit strange, but it works. So there we go, and we'll get the other formula up here in just a second. All right, so you can see that I've just changed out and put the other formula up here. Now we're parallel to the y-axis. The big change, the only real change here in the look of the formula is that now the bigger number is under y. A squared is over there. The center is still the same. It's still HK. The vertices have changed now. Instead of adding A to the x-coordinate and subtracting it from the x-coordinate, we're going to do it with the y-coordinate because that way if this was rotated, we'd be going up and down to get to those vertices. And the same thing with foci. We're adding and subtracting C from K, where C squared is still A squared minus B squared. All right, so here's our first example using ellipses. We want to find the center, vertices, and foci for this equation. X squared over 36 plus y squared over 81 is equal to 1. So when I go through this, here's what I notice first. I am not adding or subtracting anything with the x and y. So what that tells me is that h and k back in that formula are both 0. So my center is just 0, 0, which is going to make this one actually really pretty nice. The next thing I notice is that 81 is bigger than 36. Okay, well, great. That means that the major axis here is going to be vertical. We're going to be parallel to the y-axis, so that's the formula we want to be thinking about. So my a is 9 and my b is 6, because remember, these are a squared and b squared. Okay, so 9 and 6. So the vertices, we know that when we have a vertically stretched ellipse, we add and subtract a and b, or I'm sorry, a from the y-coordinates. So since my y-coordinates in the center are 0, we add that 9, we get 0, 9, we subtract 9, we get 0, negative 9. That's all set. For the foci, we need c, so I set up that c squared little equation. We know that c squared is equal to a squared minus b squared. A squared is 81 and b squared is 36. They're actually already sitting here waiting for us, so that's nice. Subtract, you get 45. The square root of that gives you the square root of 45. And so the foci then are 0, and I didn't write it out this time, but it would be 0 plus the square root of 45, which is just the square root of 45, and 0 minus the square root of 45, so the negative square root of 45. And so there's our first example. I've got one more, and it's way more fun. All right, so this one's a monster. This is going to be a lot of fun. Here we go. Find the center vertices and foci for this equation. 9x squared plus 16y squared plus 36x minus 16y minus 104 is equal to 0. Okay, that doesn't look anything like the standard form that we saw for our equations for ellipses. So we are going to have to do a lot of work to make this one happen. As you can see, I managed to fill up my entire board very messily trying to fit this all in here. What we're going to have to do is we're going to have to complete the square. Not once, but twice. Once for x and once for y. And so the first couple steps I have here are to get us ready to complete the square. Then we'll complete the square and then we'll figure out the answer. So let's do this. First thing I did is I rearranged it so that my x's were together. So 9x squared and 36x, and then the y, 16y squared minus 16y. And I don't even want that 104. I'm just going to shove it over to the other side. So it was minus, and when I move it over, it's a positive 104. Now, in order to complete the square on the x's, I know I can't have that 9 on the x squared, so I factor out a 9. That's where I get this 9 out here. And then we have x squared plus 4x, and you'll notice I left a blank, and I've obviously filled it in already with a 4, but we'll see where that comes from here in just a second. And then I did the same thing for the y's. I factored out that 16, which gave me y squared minus y, and I left a blank. I put 2 blanks over on the right-hand side because you remember, whatever you add to one side, you have to add to the other, and so I'm all set. So for x squared plus 4x, way up here in the top corner, I did my completing the square. Remember, you take that middle term, the 4, cut it in half, that gave me 2. You square that, you get 4, and that's what I added here. And on my board, it's in green. Hopefully, you guys can all see it just fine. But it is a 4. But here's the thing: we didn't actually add 4 over here on the left. You're saying, well, why not? Well, because there's a 9 here. 9 times 4 is 36. So we really added 36 when we put that 4 in there. So I put a 36 over on the right. For the y's, I take the negative 1 in the middle. I cut it in half. When I square that, I get a positive 1/4. I wrote that here. It's purple on my board. You probably can't tell. And at that point, you're probably like, oh no, a fraction. But here's the wonderful thing about this one. 16 times a quarter is just 4. So we don't actually have to really work with a fraction very much here because it just disappears and we add a regular 4 over on the other side. All right, so that gets me here. Ignoring the division here that I have. Gets me to 9 times x plus 2. Remember, when you cut it in half, that 2, that's what goes in the parentheses, squared. And I have 16 times y minus a half. Again, when I cut that negative 1 in half, I got a negative half, equals 144. And that's getting me really, really close to having this in standard form. But there are a couple of things that are still not right with it, but they're all going to get taken care of in one step. So the 9 and the 16 are not allowed. We need numbers, we need an x minus something over a number. That's what we really want it to look like. And we also need 1 on the other side. So I'm going to deal with that 1, and everything else will just fall right out for us. So if I divide 144 by itself, that gets me the 1, which you can see up there. But when I divide these, basically I'm just reducing fractions. 9 over 144 reduces to 1 over 16. 16 over 144 reduces to 1 over 9. And now I have standard form. So wasn't that fun? We got to complete the square twice. We now have it in standard form, which means we can find the center, vertices, and foci. And here we go. So from this, I can see that A is 4 because the 16 is the bigger number. Square root of 16 is 4. So I know that this one is stretched out horizontally. So my center then is -2 and +1/2. Remember, it's what makes 0 inside those parentheses. And then to find the vertices, since A is 4, I'm just going to add 4 and subtract 4 from the x-coordinates. So -2 plus 4 gave me +2.5. -2 minus 4 gave me -6.5. And that gets me to the foci. Remember, for the foci, we need C. So I set it up down here where I can find room. C squared is equal to A squared minus B squared. A squared is 16, B squared is 9. 16 minus 9 is 7. Take the square root and get C is the square root of 7. So the foci actually end up coming out even a little bit easier than the vertices at this point because you don't want to do that addition. Just leave it. -2 plus the square root of 7.5, and then -2 minus the square root of 7.5. So hopefully that works, and good luck. And yeah.